So we'll be covering properties of determinants, and in this instance, I'll be able to take a determinant of a matrix product. So let's begin with looking for the determinants of matrix A and B. So if we were to take the determinant of matrix A, let's expand by the second row. And 0 times anything will be 0. So we're only concerned with entries 3 and 2. So it's going to be 3 times the following 2 by 2 matrix, which is 1, 2, 1, 1. And remember that a square matrix is an alternating case. It's an alternating series of positives and negatives. So let's keep that in mind. And let's see here. Yeah, positive, negative, positive. Okay. And in this case, our 3 ends up being negative. And now let's concern ourselves with the entry of 2 times the 2 by 2 matrix, which is 1, negative 2, and 1, 0. From here, we can easily deduce the determinant, and that ends up equaling to negative 7. We'll then repeat the same process for matrix B. So which row would be best to expand upon? My best bets are either 1 and 2. We'll expand by, let's do row 2. So anything times 0 will be 0. So we're just concerned with entries negative 1, negative 2. So it's going to be negative 1 times the following 2 by 2 matrix, which is going to be 2, 1, and 3, negative 2. My bad, guys. And we're going to add that. We're going to add the negative 2 entry. And we're going to concern ourselves with the remaining entries at negative 2. And we have 2, 0, 3, 1. Here's something we have to consider. So I did say when you find a determinant, it is a series of positives and negatives. And over here, matrix B is no exception to that rule. So a negative times a negative will be positive, and negative 2 will be left as is. Now that we got that out of the way, we can then do the 2 by 2 determinants, and that will yield a result of 11. Now, there's one more thing we have to do, and we have to multiply the 2 matrices. Can we do that? I would hope so. So if you're watching this video, chances are you already know how to do matrix multiplication. You multiply each row by each column, and that produces a scalar value for each entry. So go ahead and pause the video. What do you end up getting as an answer? And I'm going to cut to it, and let's see if our answers are aligned. So in the first row, you get 8, 4, 1. The second row, 6, negative 1, negative 10. And the third row is 5, 1, negative 1. From here, we can then finally take the determinant of this. And if you were to expand by any rows, any of the 3 rows, you're going to get the same answer. So this is an ordinary 3 by 3 matrix. We can solve that by conventional means. What do you end up getting as an answer? And it turns out, whether you do it yourself, plug into a calculator, you get the answer of negative 77. Now, is there a faster way of arriving to that answer without doing any of the calculations? And it turns out there is a faster way. So we already know that the determinant of A is equal to -7, and determinant of B is equal to 11. And it turns out, you guys, that the determinant of AB is the same thing as determinant A times the determinant of B. This is another one of those theorems that occur in the determinant of matrix product. There's also one more theorem that we should keep note of. And let's say that we have determinant of a scalar times a coefficient matrix. That also equals the scalar to the order n times the determinant of a coefficient matrix. We're going to see this in our next example. And let's begin with that one. And with these theorems in mind, of course. So let's say we're given this matrix. Do you notice something right off the bat? And it turns out that you can't factor out a scalar constant out of this matrix. And if you guessed that we can factor out 10 out of this matrix, you'd be correct. Here's what it would look like. Sweet. And we know that the matrix be multiplied by 10. We can usually take the determinant of that. You can expand by rows either 1 or 2, but row 2 would be easier. And as a side note, the matrix determinant is 5. Let's keep that in mind. You can calculate that or do the calculations yourself. It's going to come out as 5. So let's recall a theorem that we uncovered where the determinant of A happens to equal C to the order n times the determinant of A. And n represents the dimensions of the matrix. Since you can only take determinants of square matrices, n is going to be a singular value. And in this problem, the scalar constant was 10, and we were solving for a 3x3 matrix, so n is 3. And the determinant of A, the given coefficient matrix, we already deduced that it ended up being 5. So what does 10 to the third power times 5 equal? Well, 10 to the third is 1,000 times 5. That ends up being the value of 5,000. And there you have it. So we were able to take the determinant of a scalar multiple of a matrix, and we were also able to take the determinant of a regular matrix product.